So yeah, I'm Ta-Chung. I'm from LTI CMU. Today, I'm going to present my research, and I call it toward lens extrapolatable transformers. Is my audio okay? Are you guys able to hear me
It's great on our side.
clearly? Okay, sure. Yeah. So this is my outline for today's talk. I will first talk about the overarching research goal, and then I will break my whole talk into four sections, covering basically the positional embeddings and also the lens extrapolation capability of transformers using this positional embedding. And finally, I will conclude this talk. So yeah, let me begin. So the research goal is actually quite simple. As we know, transformer language models are pretty expensive to train, partly because of the quadratic complexity of its self-attention, which is factually sequence-length. However, we do have pretty long context input in the real world scenarios. For example, we have books, scientific articles, and or government reports. So it's almost impossible to pre-train on very long sequences because it's just too expensive. So our research tries to advance lens extrapolatable transformer language models. And by that, I mean, we just train a transformer language model on short sequences. And then we expect it to perform equally well, if not better, on longer sequences. Because longer context is provided. So hopefully we wish the model can perform well or even better. And we want to achieve this goal without any fine-tuning because sometimes it's not possible to fine-tune these large language models. Okay, so that's the research goal. And let me move on to the first section. I call it uncovering latent positional statistics. So in this section, I want to first verify that positional embeddings are really the key to lens extrapolation. Yeah, we want to first verify that positional embeddings are actually the key to lens extrapolation or even the performance of transformer language model. So I started with this kind of crazy idea. What about we just throw away all the positional embeddings? Because if positional embeddings are the only length-dependent parameters, then if we just simply discard them, maybe the model can magically extrapolate to longer sequences. So why not give it a try? And another evidence is that I found this paper from Harvard et al. It's called Transformer Language Models Without Positional Encodings Still Learn Positional Information. So the idea is so simple. They just remove the positional embeddings. And surprisingly, this new model still achieved pretty nice performance on short sequences. I mean, no extrapolation. So if you take a look at the figure here, this is the no-pulse model. And the complexity is 13.1. It's actually quite close to other positional embedding methods. And Alibi was the state of the art when that paper was published. So I wanted to know a little bit deeper about this. Like, why can this model perform so well without positional embeddings? How did the model encode positional information in its parameters or architecture? Okay, so to verify that the model already captures positional information, I did a position probing experiment. I grabbed a transformer language model, which is randomly initialized, and it's frozen. And I just attach a very tiny position classifier. It's like a 2-layer MLP after all the layers. And then I just train this position classifier to predict the position of each input embedding. And also, I use randomly initialized Gaussian vectors as the input vectors because I want to completely eliminate the semantic effect present in the input. So the goal of this position classifier is very simple. It just needs to predict a number at each position n for each input embedding. And then I compute the mean absolute error between the predictions and the ground truths. Ground truth is nothing but some integer from 1, 2, 3, all the way to 512, given that the input sequence length is 512. So a randomly uniform guess of this position classifier will give us an MAE of around 128. So if we get MAE below 128, then it means that this position classifier is picking up meaningful positional information from the frozen and randomly initialized transformer language model. As we can see in this figure, no matter how many layers I use, the MAE is always below 128. So this is pretty interesting. And then I wanted to dive deeper into the architecture of this transformer language model. So let me go through some notations and assumptions. So just for the analysis purpose, I analyzed the first layer of a Gaussian transformer language model. And the reason is because if the very first layer already encodes the positional information, it can easily pass this information to subsequent layers. And also, I initialize the input embeddings and all the parameters randomly following the usual convention, which is just a Gaussian distribution with zero mean and sigma squared as its variance. Okay, so this is a quick recap. This is how we compute causal self-attention. By causal, I mean we have the causal max to prevent one token to look at future tokens. So first, we perform some linear transformation on the input embedding to get the query and value vectors at two positions, m and n. And then we compute the pairwise correlation, as shown here, the qm transpose kn. This is just an inner product if m is greater than n. And then we mask it out if q is appending to future tokens by assigning a negative infinity here. And then finally, we just compute the attention weight using scaled softmax attention function to get the attention weights. And this sums up to 1. So this is the whole process of the causal self-attention. And then in the paper, we showed that the output vector after each layer, this is by concatenating all the hidden vectors for all the attention heads, we call it OM. And this OM, when sigma is small, it actually has zero mean and a very special covariance metric. So the covariance metric looks like this. Is in the numerator, we have d squared times sigma to the 4th power. In the denominator, we have m. So d is the hidden dimension of the transformer language model. Sigma is the variance we use to initialize all the parameters. And m is the current position index. So m is something like 1, 2, 3, all the way to 512. And I is just an identity matrix. So, well, what does this tell us? It tells us that if we are given a hidden vector after the first layer of a transformer language model, we can just compute the variance of all the elements in that vector, and then we can roughly guess the position of that input embedding simply from the variance. Because as you can see, if m increases, this variance term will decrease.
Question.
So yeah, please go ahead.
Provide more intuition why that m appears in the denominator, like
yeah,
calculations that yeah.
So of course we have to go through some derivations, but the high level intuition is that imagine that what the causal self-attention does. It's when it's randomly initialized, it's actually computing the average of all the input embeddings because all the parameters are randomly initialized. So it means that its qm transpose kn will be pretty close to 0 because all the elements are randomly initialized. So they're orthogonal, kind of orthogonal. So that means the attention weight will be pretty flat. And if we have a flat attention distribution, it's pretty close to a uniform distribution. And it means that at a certain position m, the model is trying to sum up and then average all the preceding m elements. So that's why we will have this m in the denominator. Because if you take the average of more vectors, then the variance will be smaller. It's kind of similar to the idea of law of large numbers.
Got it. But are we making an assumption that our attention is causal, like it's one-sided?
Yes, exactly. This is a pretty important part. It is causal. So I actually ran another experiment in which I grabbed a Berg model, which has bidirectional self-attention, right, without the causal self-attention map. And for that model, if we remove the positional embedding, it's not able to converge to a nice perplexity, at least in my experiment. I don't know for others, but yeah. So I believe, like you said, the causal attention mass is the key here, because only if we have the causal attention mass can we perform this kind of average of the preceding m elements, and this m will change to the assumption of causal attention mass. Yeah, that's a good question.
Thank you.
Can I ask a question?
Yeah, please.
I want to make sure I understand.
Mhm.
So you only freeze the first layer of the transformer, right?
Not only the first layer, it's just for the analysis purpose. If you're talking about this figure, let's say if the number of layers is 10, I freeze all the 10 layers. I only train the final position classifier.
Okay, so
Yeah.
why I still don't understand
Mhm.
why removing the positional embedding is still working because
So yeah.
is the intuition that since you're frozen the layers and
Mhm.
each layer has some randomness in it, and
Yep.
finally it remembers this randomness, so it's a substitution of the positional embedding.
I don't think so. So it's like
Okay.
imagine you have different number of vectors and the number is n. So let's say you have n vectors and they're randomly initialized. If you take the average of them and compute the variance, and you call this variance v. So whenever m increases, this variance v will decrease. And simply because it's taking average over more input embeddings.
Okay.
Yeah, so I mean, a more intuitive way to think about this is, let's say you have a lot of random vectors, right? And once you take the average of more of them, then you will be closer to the average of
Okay,
the distribution you use to initialize the vectors.
but what if at some point
Mhm.
the average converges to the true average and it doesn't change anymore?
Oh, so yeah, so that's one possibility. But if you only average over a few tokens, then you still
Okay.
need to take into account the variance of the input vectors, right?
Yeah.
So those variants will be larger. But yeah, I think you are right. So if you go to if you push M to somewhere like 8,000 or even 10,000, then yeah, maybe you will be pretty close to the um yeah, I would say, well, okay. So if you are close to the average, then you will be close to the distribution we use to initialize the parameters, right? Which is 0.
Mhm.
And in this case, yeah, for sure, the variance is pretty small compared to maybe if we just average the first 10 tokens, because they are still far away from the average, and you will observe higher variance. Does that make sense?
Got it. Thank you.
Yeah. Okay. Good question, by the way. Um, yeah. So, well, we still need to verify a little bit. Like, is this decay invariance lemma correct or not in the real world? So I just implemented a multi-head attention transformer language model with causal mass, and then I call this model simulation. Sorry. Yeah, so for the simulation curve, I just get the hidden vectors after each layer. I compute the variance of that vector and then plot it here. So this is when decay is where sigma equals 0.2. And for this theoretical one, I just compute this variance term and then plot it on the figure. So I also changed the sigma for different configurations. And as we can see, when sigma becomes pretty small, the simulation curves and the theoretical curves match with each other. And I made a pretty important assumption that the model was completely randomly initialized and it was frozen. So how about we perform some pre-training on some real-world data sets? Does this variance decaying lemma or phenomenon still persist? So I grab a transformer language model and train on the Open WebText 2 dataset. I train for 50 case steps, so the weights are not randomly initialized anymore. And I expect the lower layers to follow the theoretical results closely because, as we know, low-level information is dependent on positions. So let's say visualization across different layers. I plot the variance of all the hidden vectors at layer 0, 6, and 11. And as we can see for this blue curve, the variance indeed decreases when we increase the position. or you can say when the sequence becomes longer. So this partially verify the variance decaying lemma. So okay, that's good for.
Sorry, I had a question on that.
Sure.
I'm a little confused by the layer 6 line there, where it
Yeah.
seems to decay, but then all of a sudden reverse course.
Yeah.
Do you have any sort of comment or intuition on what's happening there?
So that's a pretty nice question. Yeah, I try to look into why we have this V-shaped curve at layer 6, but unfortunately, I really couldn't have any explanation of this. So, well, I believe maybe it's because the model decides to focus on different amount of context at layer 6. Because if we recall, the variance decaying lemma, it only holds true when the model looks at more tokens when the positional index increases, right? If it monotonically increases. But at layer 6, maybe the model decides to look at only 10 tokens for, I don't know, token number 4,000. It only looks back 10 tokens from 3990 to 4,000. And that violates the assumption I made for the first layer, which is the model will continuously look at more tokens when positional index increases. So that's just my explanation, and I'm not exactly sure why this happens. So that's why I said I try to focus on the first layer or the zeroth layer, because I believe it should encapsulate more information that is relevant to positional information.
Sure, that makes sense. I'm curious, have you looked at like an ablation across layers? So like if you look at layers 1 through 5 here as well to see if there's like an inflection point that kind of occurred?
Yeah, I think I did that. And I believe I didn't see any smooth transition from the blue curve to the orange curve. So if I remember it correctly, this kind of inflection point or the V-shaped curve just suddenly appears at certain layers, after certain layers. And the more interesting thing is that for the 11th layer, the trend actually reverses from decreasing to increasing. So yeah, I'm not exactly sure what happens for these higher layers.
Okay, yeah, that's interesting. Thank you.
Thank you for the question. Yeah. So yeah, that's just for some analysis. And the ultimate goal of our research is how to do lens extrapolation using transformer language models. So this is the experiment result. So the no post embedding means that we just remove all the positional embeddings. And for the sinusoidal model, it uses the sinusoidal positional embedding. It's an additive positional vector, and we will add it to the input positional embeddings. Input token embeddings. And as we can see, when we increase the input length from 512 all the way to around 8,000, the no-post embedding method actually achieved lower complexity or better performance compared to the original sinusoidal method. But this is still far from perfect because it's around 1,700, and this is definitely not usable in the real world cases. So why is this the case? And I believe this can be explained by the decreasing variance lemma. So let's first convert the log variance and log position back to the linear space. So if it's log linear, then in the linear space, it looks pretty much similar to a inversely proportional curve. So when the position index increases, the variance will continue to decrease. So this also means that for all the tokens at the tail end, they share similar numerical variance, because this curve will basically plateau when we keep increasing the position indices. So it will be pretty challenging for the model to distinguish those positions. For example, it might be pretty hard to tell the difference between the 600 token and maybe the 601 token, because their numerical variance is quite similar. And as I showed, the numerical variance might be a pretty important clue for a transformer model without positional embeddings to tell the positional information. So that's why, or this is at least my hypothesis, that why the model fails to extrapolate to longer sequences. Yeah, so let me quickly summarize this section. So I will show that the variance of output vectors is an important position indicator, and it still persists at the lower layer, or at least the 0th layer after pre-training. And removing positional embeddings kind of alleviates the exploding perplexity issue, but it's still far from perfect. So I think this suggests that maybe an explicit and extensible positional embedding design is necessary, as I will cover in the next section. Yeah, so I will pause here and see if I have many more questions from the audience. Okay, let me move on to the second section.
Before we move on, I had a quick question. I should have asked it earlier. Can we define this variance a little more clearly? I'm actually confused. This variance is defined over what inputs?
Oh, so to compute the variance, we just grab the output vector after a certain layer. So let's say after the 0th layer, we will have one hidden vector for each position, right? And then we just get all the elements in that vector and then compute the empirical variance of that vector.
And that vector for a particular position?
Yeah, for a particular position.
And
so let's say yeah, sorry, go ahead.
And the size of that, the size of this average is the size of the dimension in that position.
No. So okay, let me try to explain this in another way. So let's say we have a hidden vector of dimension 128 at position 2. Well, actually we have the same dimension across all positions, but let's say we are at position 2 and we have a 128 dimensional vector. We just grab those 128 numbers and then compute the empirical variance of them, and then use that variance as the positional indicator at position 2. And then we repeat the same process for all the other positions. So let's say if we have 512 tokens as our input, then we will have 512 empirical variance values.
Got it.
Yeah.
Thank you.
Okay. So, okay, yeah, let me move on to the second section. So it's called kernelizing relative positional embedding, because from the experience in the first section, it seems like we really need some sort of positional embedding to capture the positional information. So this is the motivation. It's actually there's actually a commonality between absolute positional embedding and relative positional embedding. And why do I say that? Because this is the softmax attention function. And this is the formulation of absolute positional embedding. EM and EN stands for the token embedding at 2 positions, M and N. And then we also have the additive absolute positional embedding. It could be sinusoidal, it could be learnable vectors at these 2 positions. I call it PM and PN. So if you add them together and followed by some linear transformation and the inner product, we will have this formulation here. And the red part can actually be expanded and rewritten in the form of relative positional embedding adopted by all the previous work. So we just naively expand all the metric product here, and then we arrive at this giant terms. So the first term here is nothing but the preview vector and the key vector at different positions. And the 3 terms here, I call it K tilde of M and N. It basically models the positional information of 2 positions. However, it also encodes some semantic information from the token embedding E, EM, and EN, and also some information from the weight matrices here. So what are the other designs of this K-tail? Can we make it simpler? And the motivation of doing this is that all the other relative positional embedding methods can be rewritten in this form. So let's look at one famous baseline. It's called Alibi. And Alibi tries to greatly simplify this term into this. So K tilde is now the absolute distance between 2 positions followed by this coefficient 1/2 to the h power here. And h is the index of h heads. Suppose we have 8 heads in the transformer language model, like h is 1, 2, 3, all the way to 8. And this is the self-attention correlation metric. This is a total, this is a lower triangular metric because we are considering total transformer language model here. And this bias match, this k tilde, will be added on this self-attention correlation metrics. So this is just a very famous baseline for alibi. And now the question is, why focus on alibi? So first, it is pretty simple and elegant compared to the previous TDS formulation. And it also achieves the state-of-the-art lens extrapolation performance back at that time. And we started to wonder, are there any ideas that we could generalize alibi for even better performance? For example, why does it have to use this 1/2 to the h's power as its fixed coefficient? Is there anything special about this set of coefficients? And also, how do we connect the first and the second term? Because the first term is inner product, and this term encodes the idea of distance. So can we try to combine them together? And let me answer the second question first. So we found that we can actually think of the second term as negative distance between m and n. So this negative distance actually encodes the notion of pairwise similarity, because if the negative distance is larger, then it means that the m and n two positions are actually more similar. And the same logic applies to the first term inner product, of course, because inner product just models the semantic similarity between two vectors. So similarity is the key here. We believe these two terms, they both model the notion of similarity. And can we try to combine them together into one concept instead of two terms? So we decided to borrow the ideas from kernel methods, because the first term is a positive definite kernel. It's just a generalized form of inner product. And the second term, because it models the negative distance between two positions, so it's actually a conditionally positive definite kernel. It's very close to a positive definite kernel, but there are some conditions here. And I believe the details might not be too important here. We just want to know how to make a CPD kernel PD. And why do we need to do that? Because the sum of two positive definite kernels is still a positive definite kernel. So it provides us with a pretty nice framework to understand what alibi is doing. And maybe it will shed more light in terms of generalizing alibi using some other kernel matrices design. So we prove in the paper a CPD shift lemma, and it basically says that if we have a CPD kernel, there exists a non-negative number C, such that if we add this C to the k tilde, the CPD kernel, then it becomes a PD kernel. So this is just a theoretical result, and we will see we'll see how we can use this in the softmax function. So here we just add this C to the k tilde, and in alibi this is nothing but n minus n's absolute distance followed by that coefficient. And we also add that to the denominator, because we just add C to all the k tilde terms. So this is doable in softmax, and this is not going to change the result, because softmax is shift invariant. So if you add a constant C to all the terms, and it will just cancel out magically. And the good thing about doing this is we can now convert C plus k tilde to a new positive definite kernel called K. And this new kernel takes in two positions as its input, m and n. These are just positional indices. And finally, because we have two positive definite kernels here, we actually arrive at one huge composite kernel here. And this new kernel takes in the query vector at position m, and also the position index itself, and the key vector at position n, and the position n here. And then it just computes the regular softmax attention using this new composite kernel idea. And why do we want to use positive definite kernel? Because, like I said, it's a generalized form of inner product. And kernel methods usually allows us to to efficiently do a transformation followed by the inner product efficiently. Because if we want to do this in 2 separate steps, maybe it's just computationally infeasible because the first transformation might project the input to a very high dimensional space, and it's going to be super inefficient if we want to do inner product in a high dimensional space. For kernel method allows us a pretty efficient way of computing this. So another way of understanding this is this new kernel takes the U and the position n, projects it to a high dimensional space using some pretty complex transformations. And also it does the same thing to the P vector, and then it computes the final inner product in that high dimensional space. And the good thing about kernel method is we don't really need to know what transformation it uses, which we only need to know this transformation happens under the hood efficiently. So that's the high level idea. And another benefit of using kernel methods is that we can actually go to the literature and then find all the existing conditionally positive definite kernels to modify the second term of alibi. So for example, I just listed some facts here, and we don't need to go through the details. We just need to know there are just some existing conditionally positive definite kernels. So that's why I call them facts, because we didn't invent them. And we just grab some existing positive CPD kernels and then plug in the 2 positions M and N here. So for example, we can have the power kernel. M and N are still positions. We can take the difference of them up to the piece power and then followed by coefficient A. And if we have this power kernel, we can combine it with some other facts to get an even more complex kernel here. We get the positional difference up to the piece power, A, and 1 plus it, and then take the log of it. So this is going to be super complex, and we can make it as complex as we want because we can just mix and match all the existing kernels. So one interesting thing about this is if we take the power kernel and then we set A equals to 1/2 to the h's power and P equals to 1, what do we recover here? We actually recover alibi. So I think this somewhat explains that why we want to use this kernel method framework, because it allows pretty easy generalizations to much more complex kernel and relative positional embedding design. And this is just an illustration of the log kernel. So as you can see, it is pretty similar to alibi, except that we have the exponent here, the A, and the log computation in front of them. Yeah, so, okay. We also want to know how this new relative positional embedding methods, we call it log and the power variance, perform on the language modeling test, especially under the lens extrapolation settings. So as we can see, the proposed method actually achieved the best performance back at that time if we just increase the input sequence length all the way to 16K. The training length is always 512. So every lens that is longer than 512 falls under the extrapolation setting. So as we can see, the perplexity continues to decrease if we supply it with more input tokens or longer sequences. And we also want to know if the model actually uses more token information when the sequence length increases. So we did a position-wise perplexity evaluation. We grabbed a sequence of lengths around 4,000, and then we just compute the perplexity at each different position. As we can see, the red curve is the proposed log kernel. And when the sequence length increases, for example, when it's at 4,000, its perplexity value or score is actually the lowest among all the input positions. So I think this indirectly verifies that the new proposed relative positional embedding is actually using more token information when the sequence increases. Yeah, so let me briefly summarize this section. We use kernel methods to shed some light into the design of relative positional embeddings. And we propose 2 kernels, power and log, and they obtain pretty strong extrapolation performance on language modeling datasets. And we use the position-wise perplexity evaluation figure to show that the log kernel seems to use distant information beyond the training length when we increase the testing sequences. So the question becomes, yeah, this is an indirect evidence that the model is using more token information, but how much information is used exactly becomes the question. we want to exactly quantify the amount of tokens this model used during the extrapolation stage. And I will cover this in the next section. And I will pause here for a while and see if I have any questions from the audience.
Looks like there are no questions.
Okay, sure. So yeah, let me move on to the third part, analyzing empirical receptive fields. So as you can guess from the title, we were trying to use the idea of receptive field to measure the number of tokens used by a model. So how do we compute the receptive field of a relative positional embedding method, and of course with the transformer language model? So first, let me draw an analogy between alibi and window attention. So this is the alibi we saw before, and this is a pretty simple formulation of relative positional embedding, if we can call it that way. It's just a pretty simple bias metric that we can see here. It means that one token can only look at most one previous token, and it will simply ignore all the other preceding tokens because we just assign a negative infinity here, and this will be added to the self-attention metrics. So why do we want to do this? Because if you look at alibi, if the sequence length increases to a pretty large number, then the number here, this 3, will become super large. It might become 3,000 or even 30K. And in that case, that number is actually pretty close to the infinity term here, because this will be passed to a softmax function. And the good thing about relating alibi to window attention is that window attention allows us to easily compute the receptive field of it. So maybe we can start from window attention and compute the receptive field, and then go back to alibi and some other positional embedding methods to actually quantify their receptive field. So I have a pretty simple example here. If we have 3 layers and window size 4, then this window attention model can look back at most 12 tokens. And this is from the Transformer XL paper. So this is actually the theoretical receptive field, because it says that if we have a transformer language model with L layers, window size W, and the maximum receptive field is W minus 1 times L. It's the number of layers times the number of the window size at each layer. But as we can imagine, a model might not use this full theoretical receptive field because we're going to train this model. And it is also hard to derive this theoretical receptive field for other types of positional embedding other than the simplest window attention method. So that's why we propose to use like a empirical tool. We call it empirical receptive field measurement tool. And the high-level idea is actually quite simple. When the model is predicting the most recent token, we want to compute how many tokens the model actually uses by computing the gradients contributed by all the previous tokens. So let's say the model is predicting the 1,000th token. If only the most recent 10 tokens contribute almost all the gradients when it comes to predict this one, then it means that the model only uses the preceding 10 tokens as its context information. So that's the high-level idea. And here, I just try to mathematically write it down. We have L tokens here. And when the model is predicting the L's token, it computes all the gradient vectors contributed by all the previous tokens from 1 to L minus 1. We take the L2 norm of the gradient vector, and so now it becomes a scalar at each position. And I call it S1, S2, all the way to SL minus 1. And I normalize it by summing up all the gradient scalars. And then finally, I compute the cumulative value of that. So this is a little bit convoluted. And as we will see in the next slide, this is the illustration of that tool. So let's focus on the delta equals 0 curve here, the orange curve. So it looks like this. So it means that when the model is predicting this token, that sits at 2048, the most recent 512 token already contribute almost 100%. Well, it's actually 95% of all the gradients in terms of the prediction here. So all the other tokens from 0 to 1536, they almost contribute nothing to the prediction of the most recent token around, let's say, 2048.
Question.
And that's these, yeah.
The y-axis is the gradient norm.
The cumulative gradient. So because I normalize it, so it means that if the y-axis is 1.0, then it means that that's 100% of all the normalized gradient together.
Got it. And can you remind us what was W and delta?
Oh yeah. Sorry. I think we didn't have time for delta and W, but for delta, I just try to play with the H parameters here of alibi. So I just add like an offset delta to this H number here. And for W, it's just the window size of the window attention. So just trying to, play with it a little bit.
Got it.
But I guess you yeah, go ahead.
And basically, and are we pre-training models with different choices of W and delta?
Yes. Yeah.
I see. Okay. So
I pre-trained the model, a 12-layer model, because I don't have that many GPUs, but at least we have 12 layers, and I pre-train it for 50 base steps on 3 different data sets.
Got it.
Yeah. So yeah, that's a good question. And I am not 100% confident if the phenomenon I observed here will generalize to super large models, but at least this is the observation I got from this small scale experiment. Yeah, so I guess the takeaway message here is that both alibi and window attention only focuses on the most recent, maybe 512 tokens, because they contributed, the most recent tokens contribute a lot when it comes to predicting the most recent one or the current token. And I also apply the same analysis tool to some existing positional embedding methods. It's called rotary and sinusoidal. We've seen sinusoidal before. And the interesting thing is that these 2 positional embeddings actually look at a lot of previous tokens, because as the curve shows here, the tokens here still contribute around, from 0.3 to 1.0. So they contribute around 70% of the overall gradient when it comes to predicting the most recent one. So this seems to be a good news, because these 2 models are actually looking at all the provided tokens in the context. But these 2 models, unfortunately, did not extrapolate well on known sequences. And I believe the reason is because even though the model can look at more tokens, it was not trained to do so, because these models were only trained on 512 tokens. So when it's at the extrapolation stage, yes, it looks at more tokens, but it just doesn't know how to utilize all the additional information. And that is the idea. That is the proposed idea, I guess. We call it the alignment between the empirical receptive field and training length. So we believe that if a model's empirical receptive field is mostly covered by the training length, in our case, it's 512, then it is probably able to extrapolate, because the model learns what to do during the extrapolation stage. But from another perspective, this is actually a bad news. We'll discuss this later a little bit, because it means that the model simply discards all the earlier information. It only looks at the most recent 512 tokens, and that's why it can extrapolate to longer sequences. But let's just use this hypothesis here for now. So we see that alibi and window attention are length extrapolatable, and I believe this is due to this alignment hypothesis. And rotary and sinusoidal are not length extrapolatable, as we see here, because their ERF were not covered by the training length. So okay, so let's say this proposed alignment hypothesis is true. How can we test it? And the way I verified it is that I just try to come up with a new simple relative positional embedding method that follows this alignment hypothesis. And if this new positional embedding method can extrapolate to longer sequences, then maybe this hypothesis is true. At least I would be more confident that this is true. So I go back to the sinusoidal positional embedding and try to make it simpler. So this is just the formulation of sinusoidal. and I expand it as we saw before. So we have this giant terms here. And to make it simpler, I just completely discard this term, and WQ and WK here. So this might seem to be pretty crazy because we only have this PM transpose PM here. And you might wonder why I wanted to do this. And that's because, so let me go to this figure first. This is the visualization of PM transpose PM. And PM is just the sinusoidal positional embedding at position M, and this is at position N. So as we can see, it has a pretty nice decaying effect. So when the Y and X axis represent the positions. So when two positions are pretty close to each other, they have a pretty high bias value that will be added to the self-attention matrix. And when they are far away from each other, they will get a pretty negative value that will be added to the self-attention matrix. And that means the model will not look at this distant correlation. So this is the new relative positional embedding method, but it's just to verify the alignment hypothesis. So this is again the self-attention matrix, and we have this new PM transpose PM here, and we already saw the visualization of it earlier. And once we get this new greatly simplified sinusoidal, or you can call it a relative sinusoidal, we again plot the ERF of it. And also I plot the ERF of the previously proposed log kernel in the previous section. And as we can see, this is the alibi curve. And the orange curve is the sandwich. This is the relative sinusoidal. And the log kernel is the green curve. And the sinusoidal is the red curve. So as we can see, alibi only looks at the most recent 512 tokens, mostly. But for the proposed two relative positional embedding methods, yes, they focus around, they put like 60% of all the gradient importance on the most recent tokens, but they still allocate a decent amount of attention or gradient to the earlier preceding tokens. But it's not as extreme as sinusoidal, where sinusoidal just completely looks at all the preceding tokens. But since it was not pre-trained to do so, it failed to extrapolate. And we believe that the design of this log kernel and the relative sinusoidal sandwich is a pretty nice balance between the alibi method and the sinusoidal method. And that's also why we believe that our proposed methods can actually decrease the perplexity when we increase the sequence length. So sandwich and log are the proposed two methods, and the training length is 512. When we increase the sequence length to 2000 and sometimes to 4000, we can see the perplexity is smaller than the training length perplexity. But for alibi, the perplexity actually increases continuously when we increase the sequence length. And the same story for other positional embedding methods. So I will pause here and see if I get any questions from the audience.
I have a question that is somewhat irrelevant to this section, but it's from the earlier sections.
Okay, sure, go ahead.
So your kernelized representation of positional information, that nicely explained alibi. I'm wondering if you have also tried to use that framework to explain sinusoidal or rotary embeddings.
Good question. So first, sinusoidal in its original form is not a relative positional embedding method, right? It's actually absolute positional embedding. So that's also the motivation of making it relative, as we saw here. So this original kernel is super complex. It's definitely not a CPD kernel. But once we greatly simplify it into this is just a positive definite kernel. We don't even need to shift the kernel to make it positive definite, because this is an inner product. And for sorry, what was the next question? Yeah, rotary. And the thing about rotary is that I believe rotary is not, it's not a positive definite kernel if I remember it correctly, because it's multiplying two rotation matrices, one to the 3 vector and another to the P vector, right? They have two rotation matrices. And if you do this transformation, I believe the resulting matrix product is not inner product anymore. But I'm not 100% sure, but I believe it's not inner product anymore. So if that's the case, then it will be pretty challenging to use the kernel framework to analyze it, because the kernel framework requires to have the first term, the first inner product to be positive definite, and the second term to be conditionally positive definite. But rotary seems to violate this assumption. So yeah.
That makes sense. And maybe if we can go back to the table, I had also one question there.
This one?
This came up a couple of times earlier. When we talk about length generalization, we keep using this, I guess, phrasing that something generalizes across length. And I wanted to get more clarity on that. It seems like what we mean when we say length generalization in this context is that your perplexity doesn't go much higher compared to the length that you have trained on. In fact, here you're showing that it goes down by a tiny bit, but the margins are very small. But in some ways, I personally feel like we should maybe this is probably not a common way of thinking. I think generalization across length maybe should refer to actually being able to reduce perplexity significantly as you see much more context, right? So in some ways, if one asks me which of these methods in this table generalize across length, I would say none of them. Because even the best ones keep the perplexity constant at best. But I think in ideal world, we should really be able to see drastic perplexity reductions as we increase the context window.
Okay. Yeah, that's a pretty nice comment. And yeah, I partially agree with you, but I also want to point out that if we use the data set of natural language, it already has like an intrinsic recency bias in the data set. Because we as humans, when we are writing essays or writing, paragraphs, we have this recency bias encoded in our brains. So that means if we keep increasing the sequence length to maybe like 16K, it's just not, it won't align with how we humans think or how we write. So I believe maybe it's not possible to see a dramatic decrease of perplexity here, but that's a pretty nice question. And I will skip this and go to the last section, in which I will cover some real world applications outside of perplexity. So, Horacio, I only have 2 minutes left, but I will try to be quick. So, yeah, just like Daniel, you said, maybe the model needs to, focus on more tokens in the context, just, other than perplexity, or simply by looking at the perplexity score. So that's why I try to find some real world application, because, okay, so I also made an important assumption here. I say that practical long context tests maybe only use partial context of the overall long context. So what I mean by that is it's pretty similar to the retrieval setting. So in a retrieval setting, we have a lot of inputs, a long input, and the model only needs to focus on some of them. So this is a pretty important assumption, and I totally believe there will be some other tests that violate this assumption. For example, summarization, because in summarization, a model needs to focus on the high-level concept of the overall input. But let's use the assumption here, the retrieval setting. So what do I mean by that is, let's say we have 9 tokens here in the context. Language modeling mostly only needs the most recent 3 or 4 tokens in order to predict the last one. But if we want to do retrieval, then maybe the model has to randomly access some of the previous partial inputs. And there are also some other settings. For example, the summarization setting I just described. And there are some other artificial tests. For example, parity. In parity, we want to compute the number of ones in the long context and decide whether the number of ones is even or odd. And as you can imagine, the model has to be precise down to every single bit, because otherwise the model cannot predict whether the number of ones in the overall long context is even or odd. And we have another project on that test, but I'm not going to cover it today because that's a little bit far away from the main idea of this talk. So yeah, anyway, let's look at some concrete examples. So we have a line retrieval test here. So it means that we have a lot of key value pairs. The key is just for example, like line topic key. This is just some random words. And the key is the register content. And in the first line, it's 24169. And we just repeat the same pattern again and again and again, and all the way to maybe like 10K key value pairs. So this is very different from the data distribution of natural language or in the language modeling data set. Because now the model, when it is asked the question, what is the register content in line morning conversation, it will have to skip all the most recent key value pairs and go to this second line and then answer the register content is 10310. So this is a little bit artificial, but I think it illustrates the idea. So let's look at some baseline performance, because we expect the existing large language models to perform relatively well on this simple test, right? So that's the case for Cloud and GPT 3.5. These are some closed source models, black box models, and they perform pretty well. But for all the existing open source language models, they didn't achieve they didn't achieve good performance, as we can see here. The best one is maybe the green one here, the long chat 13B16K. So they use the idea of positional interpolation, let's say like a concurrent idea or a parallel idea to the positional embedding methods I just discussed. And the crux is that this long chat 13B16K needs to be fine-tuned on the 16K sequences. So this is different from the methods I developed because we don't need to do fine-tuning. Yeah, but anyway, this long chat model is the current state of the art on this pretty artificial and seemingly simple test. And we also have a slightly more realistic test. It's called topic retrieval. So let's imagine there is a long discussion between a user and an assistant, and there are multiple topics in this conversation. And at the end of the conversation, the user just asks, what is the first topic we discussed? And now the model needs to recall or go back to the first topic and generate the actual content of the topic. And again, we have the same competitors here. And this time, Cloud and GPT 3.5 still perform pretty well. And long chat is a little bit better. Well, it's actually pretty nice. It's really close to Cloud and ChatGPT. But we still see a performance drop at 16K. And also keep in mind, this long chat model needs to be fine-tuned on 16K sequences. So is there any potential solution? Can we try to achieve similar effect or even better performance without any further fine-tuning? Well, I think the answer is yes. And I tried to look at all the existing large pre-trained models and found that people tend to ignore the family of T5 models. And why do I want to focus on T5 model? Because it has a pretty flexible relative positional embedding design. And it has the formulation is something like this, but we don't have time, so I will skip this. We directly go to the visualization of the positional bias it learns. So T5 has some learnable positional scalars. As we can see in this figure, it means that if the current position sits at position 0, and let's say we have another position at another token at position 50, we will add like a smaller term to the self-attention metrics. So this basically means that the model only focuses on its right and left immediate neighbors. It will ignore all the distant neighbors from both sides. And for this figure, it means that the zeros token will actually focus on all the faraway tokens instead of focusing on its nearby tokens. And this one means that the model will focus on the right-hand side tokens, and this one will be focusing on the left-hand side tokens. So this is pretty interesting because this T5 model is super flexible, and I don't know why it's kind of ignored by researchers. So that's why I picked this T5 model up and then try to improve it a little bit. So there's one little issue of this T5 model is that it's suffering from the dispersed attention issue. So let's say we just grab one self-attention distribution after softmax, and we just plot the attention value here. So let's suppose the input sequence is of length 1400. We can see the largest attention value is around 0.35. And for this one, if we extrapolate to 14K 40K tokens sequences, the attention value, the largest one, will decrease dramatically from 0.35 to 0.012. So this is another mismatch here, the training and extrapolation mismatch. So can we try to boost the attention value a little bit to align the distribution during the training and extrapolation stages? That's the proposed idea. So yeah, that's basically it. We just we just adjust the temperature of softmax so that once we adjust the temperature, we will switch off the largest attention value here to make it as close as possible to the 0.35 here, even though the input is longer. So we try some alignment methods, for example, the maximum probability, and we also try to align the entropy of two distributions, the short distribution and the long distribution. So yeah, let's skip the details here. But the idea is alignment of attention distribution and their statistics. So again, we run it on the perplexity language modeling benchmark. So now, if we don't apply the fix, the original model will just explode in terms of perplexity. But once we apply the fix, it doesn't explode, but it's also not pretty great. As you can see, the perplexity still increases. But that's not the whole point here, because like we discussed, maybe perplexity or language modeling is not the best benchmark to measure the ability of lens extrapolation. So let's go back to the line retrieval test. The green curve is the Longchat 13B model, and the Flame P5 XXL model is the orange curve. As you can see, it's already better than Longchat 13B 16K without any further fine-tuning. This Flame P5 model was pre-trained using sequences of length 500 Pro only. So this is pretty surprising, and for some reason it was ignored before. And after applying the proposed fix, for example, aligned by max, we can almost achieve perfect line retrieval performance. Again, this is done without any further fine-tuning. But the entropy alignment seems to deteriorate the performance a little bit. And this is the story for topic retrieval. Again, we see similar trend here. When equipped with the proposed fix, it performs pretty well. But the original model also performs pretty well. Finally, we try to do some multi-document question answering. So this is from another paper, and then they get some questions. They get some documents and questions from the natural question or a natural QA data set. And then the answer is guaranteed to exist in one of the given documents, and the model will need to answer the given questions and given all the documents. So as we can see, with the applied fix, we can boost the QA performance. This is accuracy, 34 score is 100. With the applied fix, for example, with the max alignment strategy, we can boost the QA performance consistently across different number of documents or different sequence length. Yeah, so that's basically it. Let me quickly conclude the talk. So we saw a lot of designs of positional embeddings and kernel methods and stuff like that. And we see our relative positional embeddings perform better at this time compared to other types of positional embeddings. And I believe the crux is the alignment of training and extrapolation stages, because we've seen a lot of instantiation of the idea of alignment, right? For example, receptor field alignment. So that's why we have the power and log kernels and sandwich. And we also see the maximum probability alignment or the entropy alignment. That's when we look at P5 and try to fix it, this dispersed attention issue by this alignment strategies. So these are the supporting publications, and I also want to thank my co-authors. And that's it. I'm happy to take more questions if we still have time. Thank you.